Okay, thanks everyone. I'd like to also acknowledge my co-PI, Dr. Vijay Gopu, Civil Engineering in University of Louisiana, Lafayette. And also I have a student team called the Drone Corps who is working with me, some of whom are volunteers. I'd like to acknowledge them for their efforts in this. Yes, what we're looking at here is the design considerations and the use of unmanned aerial vehicles for the purpose of bridge inspection. The objective here, though, is not to just apply unmanned aerial vehicles to the science of bridge inspection, but to design a system that may have some hopes of becoming practical in the field of bridge inspection. And the system would involve not just the UAVs, the unmanned aerial vehicles, otherwise known as drones, but the instrumentation, replaceable components, software as well, and considering the human factors involved. We're not here going to entirely replace the bridge inspectors, not for a while. There are too many logistical considerations, constraints, and problems that have to be solved. Essentially, when we're talking about a UAV, we're kind of talking about an aerial robotic. And we know from the field of robotics already that there are many problems that have not been solved in robotics, many problems that have not been solved in AI. So we're looking at a system, and we're looking to augment what the bridge engineers do, and to gain some ergonomic, scheduling, perhaps economic benefits and safety benefits. When engineers have to go out and inspect bridges, there are safety considerations. Many of the bridge structures are quite high. There's weather that problems, there's wind, there's using special equipment to get up under the bridge deck to do inspections. The system should make heavy use of software. If we're going to go through all of this effort and put UAVs out there with expensive instruments, when we pass a bridge to do an inspection, we need to gather maximal information from that bridge. And we need to have a knowledge base that's built up over time, where this knowledge base can be used not only to gather data from the experiments and to gather data from the bridge inspection, but to actually refine the process over time. So I see some deep learning, some cloud computing possibly involved. My background is in computer engineering. That's one of the areas I'm interested in, is applying deep learning cloud computing to this field. To make, essentially, the UAV with instruments a very smart instrument. We also want to consider fault tolerance in this process, because the bridge environment for unmanned aerial vehicles is quite hazardous. Wind, turbulence, weather conditions, the bridge structure itself, the water beneath the bridge, right? These are all considerations, and some of these instruments that we perhaps want to mount on the UAV, like an infrared camera, can be quite expensive. If we lose these instruments, you drop them in the water, for example, what happens then? But the UAVs themselves can fail, so that's a consideration. And we want to look into that. What is the contingency plan for that? What is the design plan for that? So some of our methods involved, first of all, we wanted to get with the actual bridge inspecting engineers and see what are these engineers looking for? What would help them? And so what we learned here was that the engineers had especially keenly felt the need for repeated inspections. You know, they might go and actually find some problems like spalling or cracks or corrosion or rebar sticking up out of the pavement, for example. But they wanted to revisit that bridge over and over and over. I found that in the Acadiana region with DOTD, where we're going to apply this, there are 1,600 bridges, and there are only 6 inspectors. okay? So ergonomics is a big factor. When you go to the bridge, you can't just go and do an inspection at the bridge. You have to stop traffic, right? You have to plan, you have to get the equipment out there to look up under the bridge deck, for example. This is all logistics that have to be coordinated ahead of time. And these 1,600 bridges have to be inspected annually. The engineers told me that repeated inspections, time-wise, ergonomically, are a very big problem. They also may take thousands of photos. There's a need for software to go through these images and sort them out to find the most important ones and have the engineers look at that. That's a big need. We wanted to gain knowledge of projects similar to this. One of the ones we studied is the state of Minnesota. The problem with them, with that project, is that the UAV that they purchased was $140,000. We only have about $11,000 to spend on UAV and instruments. We think it can be done. And we think maybe to have a more economical UAV and instruments is probably the better way to go, because you can sustain losses. And you want to not have all of your eggs in one basket, not have all of your dollars in one basket. We wanted to also survey instrument functionality suitable for bridge inspection. A couple of things we found was that infrared is important, but also just high definition 4K video level can actually do a very good job. But we need to apply software to that to recognize images and pick out the most important ones. The infrared can help in detecting bridge road surface delamination on the bridge deck. We also need instruments that are capable of looking up from beneath the deck of a bridge and providing our own light source there. If we're going to do imaging from beneath the bridge, it's not very well lit. That's the problem. So we need to provide our own light source. We need to have instruments that can focus on a particular area while the UAV is moving. The UAVs are a special problem because we're finding that UAVs use global positioning system quite a bit, and in the absence of that signal, their flight paths, even the waypoints, become unstable, which tends to lead them. We've had some experience of crashes with the UAVs because of loss of GPS signal. When you fly a UAV beneath the bridge deck and gimbal camera upward to take images from beneath the bridge deck, you can lose a GPS signal. We have to have an alternative method of positioning for the UAV in order to be able to accomplish that task if we're going to fly beneath the bridge deck. If we're going to fly at an angle and take imaging, we're going to have better zoom capability and better tracking capability for instruments to accomplish that. Again, we have a small budget, not very conducive to purchasing multiple UAVs and comparison testing. Not all UAVs that we've looked at in that range are equal. So what I've had to do is employ a number of hobbyists, right? I had to get a number of hobbyists involved, most as volunteers, in order to have these hobbyists try out some of their UAVs for us. So I don't have to go buy it, test it out, go buy another one. I don't have the budget to do that. So I've got to employ persons and their field experience in order to help me make these decisions about what UAVs are best to employ in this project. Another thing is that, again, there are technical considerations around the bridge. One of these is the wind. The bridges produce quite a bit of turbulence, but most bridges cross bodies of water of some kind. So what happens if the UAV damages a prop or loses control and falls in the water? Right? If we got a $10,000 instrument on board, $10,000 UAV, we've got a problem. But what we're finding is that most of the electronics can be conformal coated to protect them from moisture. We may have to replace the motors, but we can also equip the UAV with a pop-out parachute and pop-out flotation devices, so we can retrieve it from the river, perhaps. Right? If we can get a hook on it, we can retrieve it. But the other consideration is that a lot of these bodies of water are pretty extensive, and so we may have to. One approach is to take this and try to fly the UAV across the entire body of water and inspect the whole bridge. Okay, but that approach may be one that's not workable practically. What we're considering is having something like a flotation device, a boat, if you will, that will keep fresh batteries, fresh UAVs, and have those UAVs use that essentially as a UAV aircraft carrier, and get the UAVs out to the correct position in the bridge, and from that point do inspections, right? So there's some reliability considerations here, but we also have to have the university being a commercial entity, we've got to have, by FAA rules, a licensed UAV pilot. And so that's one of the logistics we had to put in place. So just recently, one of my volunteer students, Eric Cerna, has gotten his pilot's license. So to wrap it up, the findings that we have are, we want to do small, inexpensive UAVs so that if we lose a UAV, we haven't lost our entire budget in this experiment here. Also, we want to have lightweight or custom-built instruments. So we're using a lot of 3D printing in order to print all of our UAV components that would ever need to be replaced, because damage is going to happen, and to print apparatus to support the instruments. We're also looking at doing separate flights with each instrument, again, for the same reason, such that we don't lose all of our instruments on one pass. But also we need to adapt all of the UAVs and instruments we use and gimballing that we use to fly, to take pictures from beneath the bridge deck. So here's an example of a bridge that we plan to fly and inspect, where the structure up above, being a drawbridge, is quite complex. Even with the most experienced pilot, and well-trained, with wind that's involved in this complex structure here, there are going to be some mishaps. We need to make sure that there's no traffic on the bridge at the time, but we also need to have a plan B in every case where you're using these UAVs for bridge inspection. We think it can be made practical. However, there needs to be a practical system, and the system involves replacements, being able to replace any of the equipment that you're using. What we plan to do is have one off-the-shelf UAV with instrumentation and one printed, 3D printed UAV with all of the custom parts. And we're going to fly and compare these two as to how they perform and what kinds of data we can get back and how we can apply software to that data. And we're going to bring this back to the Department of Transportation engineers and actually see how they can use it, how they can use it, and or what suggested improvements they might have.
Thank you. So we have time for a few questions.